All right, so this section is about connecting f with f prime and f double prime. And we can kind of look at it from two perspectives. We can look at it like we did in the previous section, looking at f as being just the y values. I'm going to label this underneath here. F prime being the slope values, and then f double prime being the concavity values. That's one way to look at it. That would be kind of like out of context, just looking at a generic graph. Of course, when we apply it to real-world situations, like particle motion, right? If we look at particle motion, then f becomes the position equation, and f prime becomes the velocity equation, and f double prime becomes the acceleration equation, right? So we need to be able to go back and forth very swiftly and adeptly from f prime to f double prime, and then backwards from f prime to f, or even going all the way from f to f double prime, or from f double prime all the way back to f, okay? That's what this section is about. So this is just a summary. You can read that, at your leisure. It just kind of summarizes what happens when we have zeros of each of them. Just worth mentioning here, the zeros of f are the x-intercepts, the zeros of f prime are the horizontal tangents, and the zeros of f double prime are your PIVs, your possible inflection values. This is just another version of the same thing from the other section. This zero looks like it kind of got cut off, so maybe we'll just fix them. There we go. Okay. Let's jump down here. This could be like maybe a last part of a free response where you're asked to sketch a graph. They haven't really done this since like the 80s, which means maybe this is the year to bring it back. Sketch a possible graph of the function f that satisfies the following conditions. So really all you're doing in this situation is you're translating mathematical language into an English language, and then using that to help you sketch the graph. All right, so what I'll do, I guess, is I'll give myself an x and y axis. There's my y axis. There's my x axis. Looks good enough. Okay, so Roman numeral 1, it says f prime is greater than 0 from negative infinity to 1, and f prime is less than 0 from 1 to infinity. Okay, so that tells us something's changing at 1. I know that, so I'm just going to go ahead and mark x equals 1. And, of course, the first derivative gives the slopes. So our slopes go from positive to the left of 1 to negative to the right of 1. Okay, so that means increasing to decreasing. Now, I don't know how it's increasing or how it's decreasing. So if you were doing this with a pencil, this is where you would faintly trace something very, very light. I'll use kind of a lime color. Let's see. Going up, going down. You can see that. So that's just giving me kind of a general trend. And, of course, I have a meeting up there at the top. We don't know anything about the function values. So if you didn't want them to be meeting, you can make that one a little lower, or you can make both of them lower, but that's just kind of a general trend. Okay, the next one, second derivative information. So this is telling us how it's going up. These are the curvatures. So I'll switch to maybe a darker green here. The second derivative is positive, so that means f is concave up from negative infinity to negative 2. So now it looks like 2, so I'll mark that as 2, and then I'm going to need to have negative 2. Okay? So now it is concave up to the left of negative 2. Well, now I can fill in, right? To the left of negative 2, it's concave up and increasing. So there's only one way to draw it, increasing concave up. Oops, something like that. All right, increasing concave up. Give it a little spin. And then it's also concave up to the right of 2. Well, notice to the right of 2, it's now decreasing. So decreasing concave up is going to look something like that. Was that a knock? Oh. Thank you. So I'm just filling that in. Printer? There you go. Oh. Blanket. Oh, your blanket. Yeah, no one was claiming it, but there you go. I remember now. Thank you. Mm-hmm.
So if we get those points on the line, it doesn't really
No,
matter?
it doesn't really matter. Yeah, they could be above or below the line. The faint line is there just to give you the trends of going up or down. Yeah. Notice there's really no information about f except in Roman numeral 3, and those are limits, not actual values. So you don't have to hit anything specifically. It doesn't even tell us up there that f is continuous. That might be something else you read carefully. It might say sketch the possible graph of a continuous function f or it might say sketch a differentiable function f. All right, so the next part, it then says it's concave down. Second derivative is negative between negative 2 and 2. So concave down, so here we go. I'll just keep it connected. Why not? Increasing concave down, and then it's going to change to decreasing concave down. So I'll just connect the dots, something like that. So I made mine continuous just because that's probably the easiest way to do it. But now I have these other things to consider. The bottom one, it says the limit as x goes to negative infinity. That's the left-hand behavior is negative 2. Okay, I think I can salvage my graph that I have because it doesn't have to be scaled the same on the x and y axis. If I just make this negative 2, I can have my horizontal asymptote here, and then I can have my green graph kind of approaching it like that, getting closer and closer. This is where, too, if you had a faint pencil line, you might want to come back and erase those faint lines that gave you the trends. Okay, so everything is looking good so far. There's only one piece of information left to make sure I get. As we go to the right, we have to be approaching 0. Well, that's the x-axis, right? So you can handle this a couple of ways. One way is to say, okay, let me get rid of that entire section, and I can still have it decreasing concave up. I'll just kind of curve it a little bit more like that. And then now there's your horizontal asymptote. So that could work. Or you could have said, you know what, I don't think I want to do that. Is it possible then to curve back up and approach it from underneath? Yeah, it would be as long as you're not violating any other restrictions that were given up above. If you're going to be doing that, notice it's going to be increasing, and it's going to have to end up being concave down. And that does violate what this says. It has to be concave up. Thank you, everywhere. So in this case, yeah, no, that's okay. Yeah. In this case, you don't really have the flexibility to curve it back up and approach it from underneath. But if the end behavior or if the concavity wasn't listed, you could do that. So in this case, it looks like we're going to have to just keep it simple, right? Decreasing concave up for eternity. So we might have come back and erased a little bit. And that's it. That would be a possible version. Again, you could take any of these sections that we had, and you can kind of, if you want to like make it crazy, you could do that, right? And you could break it up and have a couple of jumps or something going on there. It's up to you, because it doesn't say anything about having it to be continuous or differentiable anywhere. It gives us open intervals, so it doesn't say anything about out the transitional points. Oh, actually, hang on. I might have spoken too soon. It has to. The second derivative is positive, or it's negative between negative 2 and 2. I just thought of something. If the second derivative is negative between negative 2 and 2, can I have a discontinuity there at 1? No, because if I have a discontinuity there, then the derivative doesn't exist, and the second derivative then also would not exist, and then it has to be negative. So, yeah, that doesn't actually work. So I don't really see any reason to try and get crazy, So if you just draw a continuous function, probably just going to want to step away, right? You've woken up the rattlesnake, and he's rattling, and now you don't want to go in and kind of tickle him. Just back away, right? Although some people play with rattlesnakes. Why? I don't know. Anybody here, would anyone here just go pick up a snake? Anyone here? You would? Yeah. Brown? You're not afraid of snakes? No. You're pretty good at identifying them? Yeah, sometimes. Yeah. Good. I'm a wimp when it comes to two things. When I get a cold, and when I see a snake. Yeah. I won't run the other way, but I'm not going to try and save it either. And maybe that's bad, but oh well. I don't like touching them. Have you ever handled poisonous snakes? No. No? Okay, good. You are a BC student after all, so you're smart. That's good. Okay. Any questions on that one? All righty. Example 2. This will be very similar to what we just did for the warm-up at the end of a previous section. So we'll kind of go through this fast. Maybe I won't write it down, but we'll just talk about it. How about that? If the graph above is the graph of f, okay. Don't always just assume that if you're given a graph, it's going to be the graph of f prime or the graph of f double prime. Read carefully, okay? So if this is the graph of f, which you're probably not going to be given the graph of f, but you could be, from negative 7 to 7, on what open intervals is the function both decreasing and concave down? Well, if you're looking at f, you want to know where it's going downhill and curving upward. Decreasing, concave down. That's going to be from negative 7 to negative 5 and from 2 to 3. Yeah? Going down and curving down like a frown. I think that's it. On what intervals is the function both increasing and concave down? Okay. Increasing, concave down. That's going to be increasing, concave down. That's going to be from negative 1 to 2, and it looks like that's it. All right? So we're actually looking at the graph, trying to pick out those arcs of the circles. At what intervals, at what x value, Roman numeral 3, does f have inflection points? Okay? So let me get rid of the colors. That's where the curvature changes. So it looks like it's concave down to concave up at negative 5. Is there an inflection value at negative 3? Negative 5 is definitely an inflection value because it goes from concave down to concave up. Negative 3 is not an inflection value, right? It's actually concave up all the way through there. But we do have another inflection value at negative 1 where it goes from concave up to concave down like a frown. And then it looks like it again at 3, it goes from concave down like a frown to concave up like a cup. So we would just have 3 inflection values because we're looking at the graph of f. Okay, so that's, again, like I said, that's probably rarely going to happen. That would be just kind of like a review of what those things are. Because normally they're going to give you the graph of f prime and ask you about f. Or rarely you'll get the graph of f double prime and they'll ask you about f. Okay? Okay, so let's go ahead and move then to part B. Same graph, but now what if the graph represents f prime instead of f? Now we read it very, very differently. Because now the y values are the slopes of f. So where is f increasing? Well, f is increasing when the y values are positive, from negative 7 to negative 5, negative 1, all the way to 7. We got to be careful. What did it ask? Where is it increasing? Okay, slightly different question. We can say that it's increasing through the point at x equals 5, because that would be a singularity. That would be kind of like this, increasing to the left, increasing to the right. So we could say it's increasing through the point, so from negative 1 to 7. But notice if the question had specifically said, on what intervals is f prime greater than 0? Could we then just go right through 5 and say negative 1 to 7? No, because at 5 now, the derivative is not greater than 0. So you'd have to step over it. So read carefully. If it said greater than or equal to 0, yeah, now I'll go ahead and cruise right through it. So they kind of mean the same thing, but in one case, it's a singularity. We can increase through it. At what values do we have a local minimum? Justify. All right, well, let's find our critical values. We have a 0 derivative at negative 5, negative 1, and 5. That's where this graph of f prime is 0. Is this graph ever undefined? No. So those are the only 3. So at negative 5, this graph goes from positive to negative. That's going to be the location of a local what? Max, yeah. At negative 1, the y values go from negative to positive. That's going to be the location of a relative min. And then at 5, as we already said, it's positive on both sides. So that's increasing to a horizontal tangent and increasing through it. That's going to be neither a local max nor a local min. And you would say since f prime is positive on either side of x equals 5. Okay, still thinking it is the graph of f prime. Where's the graph concave up? Okay, so if this is the graph of f prime, and we want to talk about concavity, we need to look at its derivative, which is the what of this graph? Slopes, okay? So now we want to know where the slopes are positive. That's where it's concave up. So the slopes of this graph are positive from negative 3 to 2, and from 5 to 7. So those would be the intervals where f is concave up. At what value does f have an inflection point? Well, now we want the slopes to change sign. So we're going to have an inflection value of f at negative 3. Since the slopes of f prime go from negative to positive, we are going to have an inflection value at 2, since the slopes of f prime go from positive to negative. And we're going to have another inflection value at 5, since the slopes of f prime go from negative to positive. So three overall inflection values. Notice that the inflection values of f are the what's of f prime? Extrema, yeah, the local extrema. Let's state that. That's a pretty good observation. The inflection values of f are the local extrema, max or mins, of f prime. That kind of makes sense, right? Yeah. The inflection values of f are the local max and local mins of f prime. So that can help you maybe identify them a little faster. That's not going to be a way to justify it. Of course, you want to talk about the sign change in the slopes. Okay, so that's what we just did in the previous section, so that should be the freshest to you. All right, and then part C. What if that same graph now up above represented not f prime, but f double prime? All right, Chihuahua. You're going to be very limited now in the types of questions you're going to be answering, okay? Because now the y values are the concavity values. And later on we'll say that the areas under the curve are the slope values, okay? So it would just say, on what intervals is f of x both concave down? Let's just get rid of the word both. Oh, how about both concave and down? There you go. On what intervals is the graph concave down? What do you think? Where is the graph of f concave down if this represents f double prime? Yeah, -5 to -1. That's it. It's where this graph is negative. At what x value or values does f have an inflection point? Well, we're looking for this graph to do what? Change signs, yeah. So at -5, it's a PIV because f double prime is 0, and f double prime changes from positive to negative. So that's going to be an inflection value. F double prime at -1 is also 0, and the sign of f double prime changes from negative to positive. So there's another one. At 5, f double prime is 0, and f double prime changes from positive to positive. Is that going to be an inflection value? No. Okay. Is there anything good going on at 3? What does the tangent line look like at 3? Oops. Yeah, it looks like it's vertical, right? Now that would be kind of hard to tell unless there was some equation or unless they told you, okay? If they intended that to be a vertical tangent and there was no equation, they would actually tell you the graph of whether it's f prime, or f double prime, it'll say has a vertical tangent at x equals 3. And what does that mean then? That means that the derivative of whatever blank graph it represented is undefined. Yeah, so that would be a critical value of f. Okay, that would also be, if that were the graph of f prime, its derivative would be undefined. So let's go back to that one. We might have missed that one. Let's go back to, and I don't even know if I asked it. Oh, an inflection point. Yeah, we did that one here. Let's go back to B4. At what value does the function have an inflection point? If this were the graph of f prime, we can't just look to see where f prime is 0. We need to see where f prime's derivative is undefined. So let's say that was a vertical tangent. Then the derivative of f prime, the slope of f prime is undefined there. Does the sign of the slope change? The slope is negative to the left, and it's what to the right? Negative to the right. So would it be an inflection value? No. It would just be a PIV. So anyway, be on the lookout for vertical tangents. They should look vertical, but you will always have some statement that tells you that. And you're like, I wonder why they're telling me there's a vertical tangent there. It's probably because it's going to end up being a critical value or a PIV, and most people are going to miss it. Okay, so that takes care of example 2. 7 minutes. I think we can squeeze one more in here. Oh, yeah, I gave you the graph again. So let's practice the sketches here. If the graph above is the graph of F, so back to what we did on the first part, on the same set of axes, sketch and label a possible graph of F prime and F double prime. Now, we might have done this only once, okay? So here we're going forward. We're starting with F, and I want to sketch the derivative. So how are we going to use the graph? Well, I want to determine what the slopes of this function are, and on the same coordinate grid, put a y value that represents that slope. So the first place that I would look for is, where does this graph have a 0 slope? Where are the horizontal tangents? Okay? Because those are the only ones that you know for sure what the numeric value of the slope is. Those are going to be zeros, right? So if this is the graph of F, let me go ahead and put the purple there, F. Then in green, we'll do F double prime. So right there we get a 0. Right there we get a 0. And right there we get a 0. And now you can look at the slopes. Okay, so to the left of -3, this purple function is decreasing, right? So the slopes are going to be negative. So really all you have to do is kind of draw something like this. It's going to go there. And then notice between -3 and 2, your slopes are positive. Your slopes are positive. So it's going to look something like, how far do we go? We don't know where that is. Something like slopes positive. And then the slopes, oops, going back down. Sorry. We got to get back down to 0. You're trying to hit this target right here. Let me make it bigger. I'm missing it. All right, so let's think about the slope in here. We have these little tangent lines, and then maybe somewhere right in here, I don't know, the slope is the steepest, because then after that they start flattening out. That's going to be hard to pinpoint, but somewhere in there you're going to have a high point. That's where the slope is the steepest. So you can just kind of hit it like that and come back down like that. It doesn't have to be exact. You don't really know how high to go. You might want to make it smooth, so if you kind of come back over here and trace it back the other way, it can look something like that. If you have something that's a nice smooth curve, then the derivative should also be a pretty nice smooth curve, kind of like a polynomial becomes a polynomial. All right, so it's positive in between there, so make sure you have your graph above the x-axis, and then somewhere in between there, the graph is the steepest. All right, so now, if this is, let's treat that like a vertical tangent. If that is a vertical tangent, as I go to the left, the slopes are negative, and they're approaching negative infinity. So that would be a what there at 3? Vertical. Yeah, there would be a vertical asymptote on the graph of f prime if that truly was a vertical tangent line. So we'll treat it as such. And then immediately on the other side, it's coming out of negative infinity, and it's approaching 0. So it's approaching 0 like that. Boom. Put little arrows there. And then to the right, the slopes are positive, and you can just look at your tangent line. They're positive, and they're getting bigger. So I just need to draw something that's crossing and getting bigger, and then I'll stop it right there. Again, and this is kind of like a, again, qualitative, but what's important then, and let's label that f prime, is that the slopes coincide. Okay? So that would be the graph of f prime. Probably have to stop there for today. So tomorrow we'll pick up here. We'll sketch the graph maybe as a warm-up. I'll have you sketch the graph now of your green graph, and that'll give you the second derivative. And then we'll go backwards on part B. Okay? We should be able to finish this section tomorrow, especially if I don't do all of them. We just kind of make connections. Quiz probably on Monday. Let's wait till we finish this section, or at least get through tomorrow so everything starts to congeal a little bit better. And then we'll quiz on Monday. Short quiz. And then I'll give you y'all's Christmas, Calculus Christmas Carol project. Yeah.